we continue our discussion on the confidence interval estimation. Let me repeat the setup here. We are interested in the comparison of the means of two normal populations. So, we have a sample x 1 x 2 x m from normal mu 1 sigma 1 square y 1 y 2 y n is another independent random sample from normal mu 2 sigma 2 square population. These two samples are taken to be independent. So, we are interested in the confidence interval for mu 1 minus mu 2, let us call it eta. So, we have earlier found out the confidence interval for the situation when sigma 1 square and sigma 2 square are known, but in general the sigma 1 square and sigma 2 square may be unknown and we may be required to find out the confidence interval. So, we take the case 2 that sigma 1 square and sigma 2 square are unknown, but equal, that is unknown, but equal variability. Now, this type of situation may arise, for example, you are looking at two brands of certain product. So, now the variability of the say average life, for example, it may be same, but average lives themselves may be different. So, in such cases this model is useful. Let us look at the analysis of this. So, as we have seen that the sampling distributions of x bar, y bar, s 1 square, s 2 square will be of interest here. So, x bar, y bar, s 1 square and s 2 square are independent. In the sampling from normal distribution, we know this fact, independently distributed. Here x bar is 1 by m sigma x I is equal to 1 to m, y bar is the mean of the second sample, that is 1 by n sigma y j, j is equal to 1 to n. If we consider the sample variance of the first sample, that is 1 by m minus 1 sigma x I minus x bar whole square, I is equal to 1 to m, and s 2 square is equal to 1 by n minus 1 sigma y j minus y bar whole square, that is the sample variance of the second sample. If we consider these quantities, then we have the following observations, that is x bar follows normal distribution with mean mu 1 and variance sigma square by m. So, here sigma 1 square and sigma 2 square both are same. Then y bar follows normal mu 2 sigma square by n. So, if we consider here x bar minus y bar, that will follow normal with mean mu 1 minus mu 2 and variance will be sigma square 1 by m plus 1 by n. So, if we want, so this is the quantity eta. So, we get x bar minus y bar minus eta divided by sigma and root of this, that is root of m n by m plus n, that will follow a standard normal distribution. However, this involves the unknown parameter sigma also. So, we cannot straight away use it as a pivot quantity. So, we need a estimator for sigma also. So, we can get it here by considering m minus 1 s 1 square by sigma square follows chi square on m minus 1 degrees of freedom, and n minus 1 s 2 square by sigma square follows chi square on n minus 1 degrees of freedom. Once again, these two quantities are also independent. So, I can add these and we get m minus 1 s 1 square plus n minus 1 s 2 square divided by sigma square, that follows chi square distribution on m plus n minus 2 degrees of freedom. Let me define a quantity S p square, that is equal to m minus 1 s 1 square plus n minus 1 s 2 square divided by m plus n minus 2, that is pooled sample variance. If we use this pooled sample variance, then what we are having is m plus n minus 2 s p square by sigma square is following chi-square distribution on m plus n minus 2 degrees of freedom. Now, we have the distribution of x bar minus y bar minus eta divided by sigma multiplied by a constant as a standard normal distribution, and let me call this quantity as say z, and I have a quantity, let us call it say w. This is having a chi-square distribution. Another thing we can notice here is that z is involving only x bar and y bar, and w is involving only s 1 square and s 2 square, that is s p square. So, z and w are independently distributed. So, if they are independently distributed, I can look at the distribution of z divided by w by m plus n minus 2 square root, that will have t distribution on m plus n minus 2 degrees of freedom. So, this quantity is equivalent to root m n by m plus n x bar minus y bar minus eta divided by s p. So, that follows t distribution on m plus n minus 2 degrees of freedom. Now, let us observe, given the samples x i's and y j's, we can evaluate x bar, y bar and s p, and this involves the parameter eta for which we need the confidence interval, and the distribution of this quantity is free from the parameters of the distribution. Therefore, this value t can be considered as a pivot quantity, and we can make use of this to construct a confidence interval for eta, that is mu 1 minus mu 2. So, we look at the t distribution, it is symmetric about the axis, it is symmetric about 0, and so this is f m plus n minus 2 t. So, we look at the point here, this point is t alpha by 2 m plus n minus 2, and we have on the left hand side the similar point, that is minus t alpha by 2 m plus n minus 2. So, this intermediate probability is 1 minus alpha, and we are in a position to write the statement that probability of minus t alpha by 2 m plus n minus 2 less than or equal to t is less than or equal to t alpha by 2 m plus n minus 2, that is equal to 1 minus alpha. So, expanding this t and then adjusting the terms, we will be able to construct a confidence interval for mu 1 minus mu 2. So, t is here square root of m n by m plus n x bar minus y bar minus eta divided by s p, that is less than or equal to t alpha by 2 m plus n minus 2, that is equal to 1 minus alpha. So, this is equivalent to root m plus n by m n s p t alpha by 2 m plus n minus 2 less than or equal to x bar minus y bar minus eta less than or equal to square root m plus n by m n s p t alpha by 2 m plus n minus 2, that is equal to 1 minus alpha. So, this means that x bar minus y bar minus root m plus n by m n s p t alpha by 2 m plus n minus 2 less than or equal to x bar less than or equal to eta less than or equal to x bar minus y bar plus that is equal to 1 minus alpha. So, in the situation when the variances of the two populations are unknown, but equal, the confidence interval for mu 1 minus mu 2 is obtained as x bar minus y bar plus minus square root m plus n by m n s p t alpha by 2 m plus n minus 2. So, this is giving a 101 minus alpha percent confidence interval for mu 1 minus mu 2. Notice here is that since the variances were assumed to be equal, we are making use of a pooled sample variance. Now, one may ask a question that in place of this, suppose we consider simply S 1 square or S 2 square only, because in that case also we are getting a variable which is free from the, which is having a distribution free from the parameters. So, why not use only this or only this? The question is that if we use only say S 1 square, then the degrees of freedom that we will get for the t variable will be m minus 1. So, if we get only m minus 1, then in that case the interval will be having the width x bar minus y bar plus minus square root m plus n by m n. Now, this term will not come here, rather we will have S 1 only, this coefficient will not come here. Here we will have only S 1 and the degrees of freedom will be m minus 1. Naturally, the length of the interval will increase if we have less degrees of freedom. So, in order to get more accuracy or you can say more precision, we need a smaller interval with the same confidence coefficient. Therefore, it is beneficial to use more information here. Let us take the case when both mu 1 and mu 2 may be unknown. Then let us look at the procedure here that has helped us to create this confidence interval. The procedure that we adopted was that the distribution of S p square by sigma square, that is chi square, and the z variable that we utilized, that also has a sigma in the denominator. So, we were able to get rid of this. If the variances are not equal, then in the first place we will be getting sigma 1 square here and here we will get sigma 2 square. So, when we add the two terms in the denominators, I will get S 1 square by sigma 1 square and here S 2 square by sigma 2 square, and the same thing will happen with the z also, where we will get sigma 1 square by m plus sigma 2 square by n. So, in no way by taking the ratios I can get rid of sigma 1 square and sigma 2 square. Actually, it turns out that there is no exact confidence interval, that means the interval which is having the length a shortest length and as well as a fixed confidence coefficient, that means the distribution free term we are not getting. In this case, this is known as a Variance Fisher situation. So, we will consider this case sigma 1 square is not equal to sigma 2 square and unknown, that means they are completely unknown. In this case, a approximate confidence interval is proposed based on, let us call it T star, that is x bar minus y bar minus eta divided by square root S 1 square by m plus S 2 square by n. So, how this has come in the first case where sigma 1 square by m plus sigma 2 square by n was there, we have simply replaced sigma 1 square and sigma 2 square by their unbiased estimates. So, it was proved by Welch etcetera that this is having has approximately t distribution on new degrees of freedom, where nu is given by S 1 square by m plus S 2 square by n whole square divided by S 1 square by m square into m minus 1 plus S 2 square by n square into n minus 1. It is by Welch and it is known as Smith Sartor-Waite formula. So, now this need not be an integer. So, nu is rounded off to the nearest integer or integral part. That means, suppose it is turning out to be 11.37, we take only 11. So, using this one can write a confidence interval using T star, we can construct a 100 1 minus alpha percent confidence interval for mu 1 minus mu 2 as x bar minus y bar plus minus t alpha by 2 nu square root of S 1 square by m plus S 2 square by n. This will be the confidence interval when there is no information about the equality of sigma 1 square and sigma 2 square. Now, there is another situation which occurs quite frequently. For example, we are considering the comparison of the two training procedures. So, suppose there are two training procedures for certain learning. So, we select say 10 pupils and we give them instructions using one training procedure. A test is conducted to measure the outcome of that. Now, for the same set of 10 pupils, another learning procedure is imparted for a fixed period of time and another test is conducted. Now, the scores are not independent because our subjects are not independent, same set of people has been selected. For example, it could be some weight reduction procedure, like the fatty people are there and we are giving them certain weight reduction program. So, by taking certain procedure for 1 month, their weight is reducing by this much. Now, for the same set of people, another procedure is adopted, then how much weights have been reduced. So, we compare the same set of people with respect to their scores. So, here this is related to paired observations. So, here although you are saying x 1, x 2, x n say follow normal mu 1 sigma 1 square and y 1 y 2 y n, they follow normal mu 2 sigma 2 square, but actually the sample has not been selected in this way, because these observations may be paired. So, basically the model becomes that x 1 y 1 x 2 y 2 x n y n, this is having some sort of bivariate normal distribution with parameters mu 1 mu 2 sigma 1 square sigma 2 square and some correlation coefficient rho may be there. Once again we are interested in the interval for mu 1 minus mu 2, that is we want to look at the difference in the average effectiveness etcetera. A simple procedure for this is obtained by using the linearity property of bivariate normal distribution, because we know that if the random variable x y is having a bivariate normal distribution, then any linear combination a x plus b y is again having a univariate normal distribution. So, here if I make use of say observations, let me call it d I, that is equal to x I minus y I, then that will follow normal distribution with mean mu 1 minus mu 2 and some variance, let me call it sigma d square. Actually, it will be sigma 1 square plus sigma 2 square minus twice rho sigma 1 sigma 2. So, sigma 1 square plus sigma 2 square minus twice rho sigma 1 sigma 2. Let me call it sigma d square. That is not important here, because they are all unknown and we need only an estimate of this, because we are interested here in the confidence interval about mu 1 minus mu 2. So, we can make use of, now this looks like a problem of the confidence interval for a mean of a normal distribution, which we have done in the first place. So, we can consider say d bar as 1 by n sigma d I is equal to 1 to n, and we consider S d square as 1 by n minus 1 sigma d I minus d bar whole square. So, if we look at this, then we can see that d bar follows normal eta sigma d square by n, and so from here we can get d bar minus eta root n by sigma d follows normal 0 1. Also n minus 1 S d square by sigma d square, that will follow chi square distribution on n minus 1 degrees of freedom, and once again these two variables will be statistically independent. So, using this we can write square root n d bar minus eta divided by S d, that will be having a t distribution on n minus 1 degrees of freedom. Now, observe this function here, it is involving the random variables, that is the observations x I and y i's, d bars are the mean calculated from the differences, and S d square is calculated as the variance of the difference observations, and here the parameter of interest eta is appearing and sigma I squares etcetera are absent here. So, this can be used as a pivot quantity, and we create a confidence interval by writing down from the distribution of the t on n minus 1 degrees of freedom. So, this probability is 1 minus alpha, and we get x d bar minus S d by root n t alpha by 2 n minus 1 to d bar plus S d by root n t alpha by 2 n minus 1. So, this becomes 101 minus alpha percent confidence interval for eta, that is equal to mu 1 minus mu 2. So, we observe here that all these cases are differently handled, that is when we observe a sample we have to look at carefully. So, if the variance is known to us, then we have some procedure. If the variances are unknown, but we suspect that the variances may be equal, then we have another procedure. If the variances are completely unknown, then we have another procedure. On the other hand, if the sampling is not done in the independent fashion, that means we have a correlated observations, then we may arrange the data in a paired way, and then we can apply a pairing formula. So, the confidence interval for the same parameter mu 1 minus mu 2, when we are sampling from two normal populations, it is dependent upon the situation. We have to, a statistician has to carefully see that which type of method will be adopted here for finding out the confidence interval, otherwise he will be coming up with the faulty conclusions.